Okay, students, so we've talked a bit about thermal physics already. We're going to get into a slightly more complicated topic related to thermal physics, and that is changes of state, phase changes, and this concept of something called latent heat. So this video is very important in terms of understanding these more difficult concepts, and then after that we will get into the kinetic theory of molecules and thermal energy, which is even more complicated still, okay? So just to remind you guys, there are three states of matter, okay? There's a solid, liquid, and a gas. And you guys know the basic difference between them in terms of their molecular structure. A solid is a very rigid pattern of molecules, a lattice structure. Liquid consists of molecules that can slide past one another but still yet close together. And a gas are molecules that are quite far apart relative to solids and liquids, okay? Now materials can go through these three different states of matter in different ways. And when they change, when something changes state, we say that it's called a phase change. So, for example, we can go from a liquid to a solid. We call that freezing. Going from a solid to a liquid is melting. Okay, you guys know that. Gas to a liquid is condensation. Liquid to gas can happen in two ways, either evaporation or boiling. And I'll talk about the difference between those two. And then in some other more rare cases, we can go directly from a solid to a gas. That's called sublimation, bypassing the entire liquid phase. And then from a gas to a solid, that's called sublimation or deposition. We don't really deal with sublimation and deposition very much in the IB, but you should be aware that you can actually skip that entire liquid phase, okay? Now, how these changes take place depends on how much heat you add or take away and for how long. So for example, I can actually add thermal energy to a solid and have its temperature not go up, okay? And the way that this can happen is if I add just enough heat where the molecules don't break their tight lattice structure, but the whole thing is actually vibrating a little bit more. You can think of it as the molecule structure being looser than it was before, okay? Now, they have the same kinetic energy as before on average, which means that the temperature remains the same, okay? Now, if I add a lot of energy to a solid, obviously this lattice structure would then break, and then the molecules are free to move about, but they might actually have the same kinetic energy as before, which would be the same temperature as before. Now, how can this possibly happen? Okay, well, to think about this, you want to think about ice. Okay, ice is something that we all have had experience with. Okay, you can add heat to ice. Okay, there's my positive Q to ice. Okay. And let's say that the ice is well below 0 Celsius. Let's say it's 30 degrees below 0 Celsius. I can add heat to that ice and have it not melt, and I can raise the temperature from 30 below 0 up to 0, and only when it gets to 0 would it actually physically start melting and turning into a liquid. So I'm adding heat, but the phase doesn't change, okay? Now, once it's at its melting point, any positive heat which I give it does not increase the temperature until the full phase change occurs. So if it's a mixture of liquid and ice, of water and ice, it's still not going to change its temperature. Okay. Now, if I keep adding it to liquid water, obviously that's going to eventually get up to its boiling point. Once it's at its boiling point, any additional heat does not increase the temperature until, again, the full phase change occurs and all the water vapor becomes steam. Okay, then I can obviously add more heat to the steam, and when I do that, the actual steam will actually increase in temperature. So the bottom line is that when the state of matter is changing, there's no temperature change that takes place because it takes energy to actually break those molecular bonds and actually change the state. It's very, very interesting. Okay, I told you I'd talk about evaporation and boiling, so here I go. Okay. When you boil a liquid, obviously that only occurs when you're heating it. Okay, all molecules vibrate more, so it's looser. They all have the same kinetic energy as before, and the temperature remains the same until all the liquid is gas. If the temperature of the gas will rise if heat is applied still further. I just talked about that. Now, how is this different from evaporation? Obviously, evaporation doesn't happen, after a rainstorm. Puddles don't evaporate because they boil away. That would be ridiculous. You've never observed that on the surface of the Earth. It occurs naturally as the surface is exposed. What happens is that the reality is that molecules in liquids move at a range of speeds. If the faster ones are near the surface, they can actually escape and become water vapor and go off into the atmosphere. Okay? If this happens, the average kinetic energy of the remaining molecules is actually reduced. So therefore, the puddle that's left on the ground has a lower temperature, and the rate of evaporation increases as the surface area increases and or the temperature increases. Okay? So that's why when the sun comes out, the puddle will evaporate more readily than if it's cloudy, okay? And also the humidity of the air above the puddle makes a big difference, okay? All right, so we're going to graph some phase changes. Now, if you have a good grasp of what a phase change does, and as well as my discussion about how heat, adding or taking away heat, can change the temperature, but not always, this diagram will not surprise you, okay? This is called the phase change diagram, and you see these a lot in chemistry and physics, okay? And what we're looking at here is we're looking at, it's a graph of temperature against heat, okay? So energy is being added, and we assume that it's being added at a constant rate. So along the x-axis, the more time that the object spends in any particular part of this phase change diagram corresponds to a larger sort of segment of the x-axis. I'll talk a little bit more about when time is on the x-axis as opposed to heat. Nevertheless, okay, if we start with ice, here's our ice at 30 below zero. If we add heat to it, okay, the temperature will go up, but it still remains ice, okay? This right here refers to the ice melting. Here it's a mixture of ice and water. Okay, here the water warms up. Here the water boils. It's a mixture of water and steam. Okay, and then here the water vapor warms up. So let me break up this diagram a little more explicitly for you. Okay, it's a solid only. It's ice here. Okay. It's solid and liquid in this flat part right here. That flat part tells you that it's solid and liquid. Okay. When the graph becomes non-horizontal, then it's a liquid only. Here it's a liquid and a gas, and here it's a gas only. Okay, so if you think about the relationship between heat and temperature, what I talked about, and how it actually takes energy to break those bonds and to change phase, this diagram will make sense to you. We'll work a little bit more with phase change diagrams and some examples. Okay, so things to note: when the state of matter is changing, the graph is flat. It takes less heat to melt than to vaporize. Very interesting, okay? Notice how, notice the difference in the slope. We will talk about gradients of phase change diagrams in just a bit, but you want to compare the gradients in these two parts. It takes less time to melt than to vaporize, okay? So anyway, less heat, less time, comparing gradients is very important, okay? All right, so I want to talk about this concept of latent heat, all right? If you're familiar with the term latent refers to something that's kind of hidden, like if you have a latent talent, it means that you suddenly discover this amazing hidden talent that you didn't know that you had before, okay? Same idea in physics with specific latent heat, okay? This refers to the amount of heat required to change the state of 1 kilogram of a material without changing its temperature. So you can get a sense of how it kind of infers something hidden, or like energy or heat that's hidden. The SI units are joules per kilogram, okay? All right, so generally, because of this definition, and the symbol is big L, L is Q over M, where Q is heat and M is mass, okay? All right, rearranging, we get Q equals M times L. Phase changes take place at different temperatures for different substances at certain pressures. Okay, so latent heat is not only the hidden energy, but you can think about it as the extra energy needed to change the state after heating. Okay, and there are two different kinds, and this is very, very, very important for you to understand the difference between them. Number one, if you're going between a solid and a liquid, either way, we talk about the specific latent heat of what's called fusion, okay? If you're going between a liquid and a gas, either way, it's called the specific latent heat of vaporization, okay? And that's L sub V and L sub F respectively, okay? So depending on the situation, you might, there are actually two different versions of this particular equation right here, Q equals ml. You could say Q equals ml sub f, or Q equals m times L sub V, depending on the situation. Again, whether you're going between a solid and a liquid, or vice versa, or a liquid and a gas, or vice versa. Okay? All right. So, again, this segment right here would then refer to latent heat of fusion because we're going between a solid and a liquid. Here's latent heat of vaporization because we're going between a liquid and a gas, okay? And again, remember that in general, L is Q over M, so it's joules per kilogram. So I want you to compare the amount of time spent, and remember, this can actually be time on this axis, because heat is being added at a constant rate. Compare the amount of time spent in the vaporization phase and the fusion phase, and you'll see that clearly for all, in fact, this is for all substances, that L sub V is greater than L sub F for all substances. Now, why would this be? Okay, so L sub V is greater than L sub F, okay? That must mean that it takes more energy to vaporize something than to melt it. And if you think about the chemistry involved and what happens to those molecules when you're vaporizing something, it makes sense because you have to put a lot more energy into something in order to get its molecules to actually physically separate from one another and become that much less dense in the space that it occupies. So it actually makes a lot of sense, okay? Here's some latent heats of fusion and vaporization, some comparisons between some common substances and some not so common. Are there any trends that you see? Okay, so there you go. You can see that L sub V, this is very interesting. Look at the boiling points, look at the melting points. Okay, there's your L sub V is significantly greater. It looks like it's greater than L sub F by a factor of by an order of magnitude of about 1, okay, about 10 times. Very interesting, okay? Okay, let's do a couple of examples. Okay, number 1, how much steam will release 1130 kilojoules when the steam condenses at the boiling point of water? Okay, well, what equation would I use? Well, Q equals ml, and in this case, it's L sub V, latent heat of vaporization. I solve for m, okay, I get it's about a half a kilogram. So you can see that mathematically, this topic is not very difficult. It's a matter of conceptually knowing which version of the equation to use when. Example 2, how much energy is needed to change 4 kilograms of ice at negative 25 degrees Celsius to steam? Wow, that's interesting. Well, that's gonna take a lot of energy, right? Because first you have to melt the ice, then you have to boil the water, then you have to boil all the water away. Okay, interesting. This will take 4 steps, okay? And what we have to do is we have to add individually the amount of energy taken in each step to get the total. So for example, what I do is I just explicitly break it into 4 steps like this. I say from negative 25 to 0, Q equals mc delta T, because it's all the same, it's the same phase, it's all a solid, okay? I got that's 206,000 joules. To melt the ice at zero, then I would use Q equals ml sub F. To go from the amount of energy from 0 to 100, that is to boil all the water, is Q equals mc delta T. And to vaporize the water is equal to Q ml sub V, okay? And I get 1.2 megajoules as my total, okay? So this is a very common kind of problem that you'll be required to do. I highly recommend that you actually explicitly break it up into steps for each, because it will get a little bit confusing otherwise. You don't want to cut any corners or go on any shortcuts with these problems, okay? Okay, I want to finally relate latent heat and specific heat capacity, okay? So here's a phase change diagram. From this graph, could you determine the relative sizes of specific latent heats and specific heat capacities? And again, we're assuming thermal energy is provided at a constant rate, okay? Now, I want you to note that if I start off with Q equals mc delta T and I divide both sides by delta little t, which is time, okay? Note that delta Q over delta T is power, and delta T over delta T is the gradient of the graph, because I'm graphing big T against little t, okay? So, if I solve for the specific heat capacity, okay, this ends up being this expression right here, and that's power over the mass times the gradient of the graph, okay? Now, of course, IB wants you to always understand what gradients mean physically. Here, the gradient can be very, very important in terms of problem solving. You can get that idea, okay? Just a quick note, again, the independent axis can either be heat or time. It's the same thing physically, because if it's heat, it's always heat being applied. It's always heat being applied at the same rate. So the phase change diagrams will tend to look the same, even though the axes are can be slightly different, okay? Now, I want you to note the phase in which the rate of temperature change is the largest has the smaller specific heat capacity. That's a very important problem-solving insight, okay? The transition that lasts the longest has the largest latent heat, okay? I talked about that. The specific heat capacity is undefined when the material is a mixture of two phases. Why is that? Because it's C is inversely proportional to the gradient. So when it's flat, that would be undefined because you're dividing by zeros. This is such a cool topic, okay? When the material is changing state, again, use Q equals ml. When it's not changing state, just use the old-fashioned now Q equals mc delta T. Okay? For example, if I heat 1 kilogram of water in a kettle and I graph the temperature against time, I might get something like this. Okay? If we continue to heat the water, it will boil at 100 degrees Celsius. Okay? Now, let's say that it takes 480 seconds for the water to actually boil. Okay? Once it gets to 100, it will start boiling. Okay? Right here, it's a mixture of liquid and vapor, right? Okay? We can actually then calculate the power delivered to the water from the second graph. And the gradient of the second graph is delta T, change in temperature over time, change in time, and Q equals mc delta T. So the rate at which we add heat, which of course is energy per unit time, and in units, that's a joule per second. Okay, that's power equals mc, change in temperature over time. Okay, now that's mc times the gradient. Notice that, do you guys remember the quantity m times little c? That's also called the heat capacity or thermal capacity. We can also express it as c times the gradient. In any event, the gradient in this case would be 100 minus 20. Okay, that's my delta y, over 480, which is my delta x, and I get 0.167 degrees Celsius per second, okay? Therefore, the power delivered, I just then put it back in this equation. It's mc times the gradient, and I get 698 watts, okay? Turns out that the power rating of this particular kettle would then be 700 watts, or 700 joules per second. So cool. Now, we're going to do a really cool activity in class where we're actually going to be dealing with, I think it's a 500-watt kettle. I can't remember what it is. And we're actually going to verify all of this, and we'll make some graphs to see how this works in real life. Now, assuming the kettle is still delivering 700 watts of power after 480 seconds, for another 480 seconds, bringing us out to 960 seconds, okay? Since P equals Q over T, the total energy supplied between 480 and 960 would be power times time, okay? And that's 3.36 times 10 to the 5 joules. We can then calculate how much water turned into steam during this time interval, okay? By using Q equals mL sub V and solving for M, I get 0.15 kilograms, okay? So very, very clever way to use a graph to help you solve a fairly complicated problem that otherwise would be, well, it'd be a lot harder to solve if you didn't have this graph, okay? 15% of the water has been converted to vapor over this interval because we started off with 1 kilogram. Okay, let's try this example. Phase change diagram, classic IB phase change diagram. Usually they would not label each part as solid, liquid, liquid, vapor, and so forth. Okay, pause the video and try this one on your own. They're asking you to find the latent heats of vaporization and fusion and the specific heat capacity in the solid phase. Okay. So note obviously that C is different for different phases, which is why they have to be specific. If they say find the specific heat capacity, that's actually a dumb question because it's different depending on the phase, okay? To find C, I use Q equals mc delta T, okay? Delta T is from the graph. Delta Q is from the graph. I got 1.4 times 10 to the third joules per kilogram Kelvin, okay? To find the latent heat of fusion, okay, I'm using Q equals M times L, and I get 100,000 joules per kilogram. Latent heat of vaporization, I got 200,000 joules per kilogram. Okay, make sure that you can do such an example as this and know which type of equation to use in which situation. Okay, I think this is our last example. Okay, this one has to do with solar radiation in a pond, in the outdoors, in nature, which is what we really love. Okay, go ahead and read this question very carefully before you see my solution. This will take you a little while to do. Okay, so we have solar radiation incident on a pond. I give you the area of the pond. The pond is covered by a layer of ice, which is 3 centimeters thick. Temperature of the ice is 0. Okay. Density of ice is 900 kilograms per cubic meter. Deduce that the mass of ice on the pond is 320 kilograms. Interesting. This is actually a pretty simple problem here. So we got to find the volume and then the density, and then you find the mass from that as 324 kilograms. Okay. The average power per unit incident on the ice over a period of 6 hours is 340 watts per square meter. Okay. Deduce that the energy incident on the pond is, okay. Well, that's pretty easy, right? Okay. 340 watts per square meter. Okay, that's a joule per second square meter. Okay, just do the math. You actually could use the factor label or the bridge method for this if you wanted to. 8.8 times 10 to the 7 joules. Continued. The specific latent heat of fusion of ice is 330 kilojoules per kilogram. Determine whether all the ice in the pond will melt in the 6-hour time period. Okay, well, you have to find the mass of ice that would melt under these conditions. Okay, and I get 270 kilograms, but since there are 324 kilograms, not all the ice will melt, and it will probably end up actually looking something like this, like a bunch of little mini icebergs in the pond.